Good morning, good afternoon, and good evening, everyone. So today I'm going to be talking about my extension on my previous question here, which was about the logistic model. So just a brief recap of what the logistic model is it looks something like this. Oh no, not that one. Like this, right? So we have some sort of differential model where this town has 5,000 people, population size is constant, and as we go or as our population increases or the number of sick people increase, then it will, at the end of the day, or at some point in time, as time goes by, it's going to plateau because that's the carrying capacity. So when it reaches 5,000, it won't exceed 5,000. So that was the idea of the population model. And then my extended question here was, what if we make it some sort of function, right? So what if we make the logistic model as a function that varies, right? And apparently this is not solvable using separable differential equations. So I used a solver in code pretty much. And here's what it's able to come up with. So as my population goes up, the moment it intersects my carrying capacity, that's when it starts to plateau, right? And so I've decided to kind of apply this in my everyday life since I have my resident dining plan. And so here's what I came up with. I have a resident dining plan. And the idea is that, okay, I'm going to make B my balance. So that's my current balance. My R is my spending rate or how fast I spend per day. So I'm going to do this per day. And then my K here, my carrying capacity, is also a function that tells me what should be my limit. So this one, instead of it going up and reaching its limit, here it's kind of going down, right? So it's the same as the previous one. It's going down. And here it's good. It's kind of going to tell me how I'm going to be able to analyze if I'm beyond or below or exactly at the balance that I needed to be. So it's kind of like an indicator that tells me, okay, for this day, I've spent enough, or I've spent less than what needs to be spent, or I've spent more than what needs to be spent. So it's kind of like, again, budgeting. It's a budgeting plan using a logistic model, right? And so here's basically how we're gonna do it. I'm actually gonna do a write-up for my presentation later. But okay, so here so I'm gonna do a conceptual motivation behind it. So what's the motivation behind it? Well, in simplest terms, actually, my motivation behind this is I want to find an application of math. So that's the deeper meaning. But moreover, I just want to budget how much more do I need to spend or how fast should I spend per day. So it's going to help me kind of simulate that idea of how fast I need to spend each day because I want to be able to get my resident dining plan to zero before the next quarter starts, at least here at my university. Because if I don't spend everything in my dining plan, then it's gonna be gone. It's gonna disappear. It's gonna go somewhere. And we don't know where that's going. So might as well spend everything, right? And so, okay. So just to kind of summarize what this is exactly. So the logistic differential equation. Yeah, what is this? The logistic differential equation is commonly used to model. So it's used to model population growth, right? So it's more common for growth of a population with some maximum sustainable population, right? Because we cannot have infinite people in a country. We cannot have infinite people in a city or something like that, or else that's just not possible. There has to be some limit. to how much people we can have in a place, right? Or any place, actually. And so we call this the maximum sustainable population, also known as the carrying capacity. Right? And so in this context, actually, what I'm going to do here, so in this context, I'm actually going to reverse this idea. And instead, we're going to do some sort of budget analysis. So we're actually reversing this idea. Let me, so reversing this idea. Emphasis on reversing. The idea to model budget consumption, right? So here are the characteristics of this model, or what this model is going to do. The balance, well, here kind of, it's also the assumptions, I would say. So here, assuming we're actually spending, right? And so definitely our balance would decrease over time. And we know in a dining plan, or at least in my dining plan, right? We cannot put money back in there. So we can't put money in there. So that means it's bound to either decrease or just stay as it is or be stagnant, right? So it's either one of those. But we cannot add because I have two ways to spend my plan. It's either I use my resident plan because I'm a resident here, or I use my we call it like a husky plan, which is basically where we can deposit and withdraw and spend. So both can be used for spending, but only one of them, so the husky plan, that's where we can deposit some money. So it's kind of like your own bank account ish. But for the resident dining plan, that's already it's part of the tuition. And so that one we cannot really put money in there, you know. So it's either bound to decrease or just stay as it is. But here I'm going to assume that because this is honestly also for myself, I need to budget and see how fast should I spend. But if I don't do it, then it's gonna simulate a new thing, right? So it's just a reminder that okay, maybe if I don't spend anything today, then my rate would probably be faster or something like that, right? And so, okay, what else are the assumptions? There's a finite budget. So in math, there's the concept of infinity and infinite. So here, there's the finite budget, or what we call the carrying capacity. And so this will tell me, okay, here's my budget for the day, here's my budget for the day, right? Something like that. And then here, the spending slows down as the balance diminishes, right? So we'll talk about that in a bit. But something about slowing down tells us a bit about calculus, analyzing change and stuff like that. So here, the spending slows down as balance diminishes. So if we have a lower balance, well, definitely our rate or how we should spend the rest of our money should be a bit slower, right? Or else we won't have enough for the whole. That's also another thing, right? We won't have enough until because I'm planning to do this budget this until August 24 specifically because that's when my quarter ends. And so if I have nothing to spend from let's say like August 20, August 20, well I'm broke. So might as well do some math on that and make sure I actually balance it out and get to zero. Ideally get to zero at exactly August 24 or else I would have to use my credit card and buy somewhere else. But but bottom line is I have to spend all of it before the quarter ends, right? Okay, so here balance diminishes, right? Or decreases. I don't want to use the word diminishes. And from there, the carrying capacity itself also decreases as we approach the deadline. So that's going to be because here at the University of Washington, at least here in Seattle, where I'm studying, is it's a quarter-based system. So we have fall, winter, spring, and summer quarter. And by the end of each, or not each quarter, by the end of summer quarter, my resident plan or my balance there will actually be gone if I don't spend all of it. And I don't know where in the world that money is going. Probably someone's gonna spend it somewhere. I'm not super sure. But the idea is I have to spend all of it before the quarter ends. Right? And so that's the idea. So the carrying capacity will decrease as it approaches the deadline, and we should have less money remaining each day. And so here's the math behind it. So that's the motivation behind it. Here's the math part. So, okay, I'm just gonna write it like that. So again, here I'm just making like a write-up so that I have something nice to present later. I might even show this video, but we'll see, we'll see. We'll see how it goes. So here I'm gonna say my BFT, so that's a function. As time goes by, that's my current balance. My dining account, oops, balance, we're gonna say in dollars. And then this is per day. So we're gonna make it a particular day. At this particular day, this is my balance. At this particular day, my balance decreased by this much, right? So that's the thing here. Okay, another variable we're gonna use is B naught. This is just gonna tell me my initial balance, and so that's day 0. And so that's also the same as B of 0, right? Same thing. And then KFT. So this is my time varying carrying capacity, right? And my expected total balance at day T. So here basically at this particular day, this should be my balance, right? So here we're still using it as sort of like a limit, but it's more of a decaying model. So let's say at this particular date, this should be my balance. If the moment, so we know how when we spend, it's not really exact per day. So we can't be like, okay, for this day, I'm going to spend $20. For the next day, I'm going to spend $20 again. We can't consistently spend $20 a day. So we have to sort of measure that. So here, let's say if I don't spend as much as I did in the previous day, then this would also adjust, right? Everything in this model adjusts is going to adapt your spending, right? Okay, so that's my carrying capacity or my expected total balance at that particular day. And then here, my R, I'm gonna call this my spending rate. And this is gonna be fitted to data, which is something actually, to be honest, I'm still working on right now. I haven't done stats. I feel like this is a stats thing. I haven't done stats before, and I will make videos on statistics. I don't know how to make models, or as of now, I don't know how to make models that will improve its precision. I would say, not accuracy. I would say nothing's accurate. I can't make a model that's precise and that learns from data. So that's something for me to learn in the future. Right now, I can only make theoretical models based on fundamental principles of life, basically. But yeah, so like this logistic model is used for measuring population. So I'm just trying to kind of tweak it, maybe make it something about my budget. But again, still not 100% sure on this idea. So this is my model. So the model is as follows. So dBdt, that's the rate of change of my balance, which is measured by my spending rate times my balance at that time, 1 minus. So here I'm copying that sort of logistic model thing. There we go. Right? Oh, actually, this is a bit, I think I messed it up, kind of. Oh, no, I didn't. Okay, cool. I don't think I did, right? Let me double check. Because I have a code to back this up, which I'm gonna show later. Let me see. I don't think I messed it up, no? Let me see my code. I don't know if my R is supposed to be negative. I feel like it should be, though. Oh, it isn't. Okay, cool. So it's not, yeah. So it's not negative. Okay, that's nice. Okay, nice. So here's what I'm gonna do. Right. So I have that. And then here, so that's my model, right? Additionally, my KFT is gonna be equal to my B naught. So my initial balance, 1 minus T, then maybe a capital T here or something like that. So here, T is basically the number of days between my first transaction and the target end date. So my first spending. So I've only got data from July 28th, I think. Let me double check. I forgot. I think it was July 28th where I started modeling this thing. Oh no, I'm scrap that. July 7, not July 8. All the way to August 3. Right now it's August 5. So I'm actually gonna update this data so I can get those in. And we'll see how the model behaves after. So that's also something I'm looking forward to doing. And then, so yeah, it's difference between my first day of transaction all the way to my target end date. And I think this was August 24, 2025, right? Because I think that's when the quarter ends. Right now, as I'm making this video, it's August 5. Let me just double check. When my summer quarter ends. I think, yeah, I think it was August 24. Mm-hmm. I have spring here. Oh, that's autumn. Yeah, I don't have. Last day of classes is. Oh, it's until August 22. Ah, that's fine. It's just an estimate. Yeah. We'll say August 24 just to make it super, super sure. But yeah, we'll see. Also, I did spend a lot today, so let's see if that affects the model. I'm also gonna check that one. Okay, so that's that. And what happens here is this makes K of t linearly decline. That's also something I want to add. From So ideally, I wanted it to be from B naught to zero. But my model is having a hard time doing that because I'm also fitting the data, I think. So that's something I need to work on, right? So this is an ideal situation where my K should decline from B naught to zero. Okay, so we did some model implementation. Mostly I did this using Python. I'm not sure if I have to write it though. Or actually, no, I don't need to. Yeah, okay. Let me see. I'll just write it. Yeah, so basically I implemented this. So here's how I implemented it. I'm also just gonna get screenshots from what I did here. So data pre-processing, that's one thing I did. And so I basically loaded and cleaned the data, right? So all of that coding stuff. Oops. I said data twice. She only said once. So I loaded and cleaned UW dining data. So that includes the basically the dates, the balances, overall just the transaction history. Okay. What else did I do? I converted timestamps. Okay, maybe I shouldn't really write that. That's just a coding thing, right? So basically, I pre-processed the data and stuff like that. And then so I basically just coded it up, the models. Oh, so here's something I need to tell them, or at least the when I present later. So here I define the logistic decay model. So what I basically did here was I used, okay, I'm actually going to go to my code and don't know why I muted myself. Okay, so I'm actually going to go to my code here and let me actually quickly share this. I think I can share it. Let me see. Yeah, I don't like showing code because it's too much stuff to remember. But what I basically, yeah, when I present later, I'm not going to show this. Here, I'm going to show this because I'm kind of explaining what I did here. I might show this later to them, but we'll see. We'll see. So here, Yeah, I just imported libraries. This is where I said about loading this data. I got from a CSV file, which is there. I got from my own account. And then I cleaned the data, right? So that's the data cleaning stuff. And then here are like the first couple of points. So here, as you might notice, it tells me what date, what time, what's the charge, and what's my current balance, and where did I spend it on here at my university. And then I plotted the data. So here we can kind of see a pattern where it decreases, and obviously it will, because don't worry, I'm spending. I'm not, I don't want to leave it stagnant, right? And here you might notice where there's some gaps. Well, that's when I didn't really spend. Okay, so and then here I created the time and days since the first transaction, define parameters for the model, stuff like that. And then here's where I kind of define the model. So here's my KFT, right? Here's my KFT. Here's the logistic decay. So that's actually okay. I'm gonna screenshot this actually, and then I'm just gonna show this thing here. Not sure if I should show code though. I don't know. Is it presentable to show code? I don't think so. I'll just show it. And then I also used a Python solver, which is solve IVP, if that's a thing, which is from the SciPy library. I'm pretty sure I imported SciPy. Yeah, here. And this is the thing, solve IVP. And what this basically does is if I go to the internet, where is the share this? Here's what solve IVP does. So I don't know why I'm showing this. This is just something I would I would use. I shouldn't really show this, but it's okay. So I used the SciPy library in Python. I downloaded that library, and then I used the solve IVP. And what this basically does, it solves an initial value problem for a system of ordinary differential equations. So apparently the model that I came up with was an ordinary differential equations model. And I haven't taken any differential equations class. I've only done intro actually. So I kind of cheated here a bit. I told Python to just go for this and solve it. I don't know how it's solved handwritten. I don't know. I might take I might take a course on differential equations. Learn about I'll probably learn this ordinary ODE. Then there's also PDE, which is partial differential equations. So these are two things I haven't learned yet, and I'm planning to, because I think it helps to learn these to better understand how to simulate behaviors of systems, right? And so it's basically this. It numerically integrates a system of ordinary differential equations. I only know how to integrate a separable differential equation, so one that can be separated, right? And I did show that in some of my previous videos on population dynamics, but I don't know how to integrate when I cannot separate it. Let's say if it's an ODE, stuff like that, right? So that's still something I'm working on. Okay, I'm gonna share back to my code here. It looks nicer. I don't want to show that. Okay, so there, that's the idea. Am I showing the right screen? Yeah. And then I plotted it using, well, yeah, another library, Plotly. And here we can actually hover and you can kind of see the balance as the date goes by. And so I got the data from, yeah, July 7. Here, you might notice why there are different July 7s. Well, these are just the time. And so basically my current balance would be 1142 as it, yeah, so that's how much I spent. I spent like what, $20. Okay. And then yeah, so here's my balance, and then here's the date, and then as of August 3. I'm gonna add more data because it's August 5 now. I did do some spending actually. So yes. And then created the oh, I already showed this. Yeah, this is the one I was gonna present. And then okay, this is something I'll get to in a bit. Oh, there's also something I'm gonna get to do in a bit. Okay, let me go back here. So that's how I did that. So yes. So here what I did was I used Python's solve IBP library. So I basically used code to solve my equation. That's it. I solved my equation using code pretty much. Here I just defined the two functions, but I don't think, yeah, I think I kind of like explained it a bit on how I did it. I think it just automatically solves the thing, right? Also, I did use it. Okay, I'm actually gonna show that part later. I'll do it later. So, okay. And from there, I also solved the model with a given R. So here, this is something that was crucial to me at least, is how we get R tells me how to fit the data, or I mean, how to fit the model to the data, right? So I can't just quote unquote guess it. I need to kind of, so here I'm going to say use code to solve differential equation. So I kind of did it here. Oh yeah, let me just say it, as well as solved for R to better fit model the data. So I used code to do both of the like the heavy lifting, I would say. So here, this is how it looks like. Let's see. So here's basically how I did it. Okay. Let me take a screenshot of this thing. Mhm. Oh, wait. So I actually did it in reverse. So I solved the model first, or I made code to solve the model first, and then that's when I solved for R. So I'm also getting a bit used to the coding stuff. I haven't done coding in a while. So yes, that's what I did, yeah. So I used code to solve the differential equation as well as solve for R to better fit the model to the data. Yeah, that makes sense. So I'm actually just gonna show the whole thing because I don't wanna. Mhm. I don't know if they can read this thing. See, that's my worry. Actually, no, I don't think I should show it. Yeah, I'm not gonna show the code. Yeah, never mind. I'll just do it. Yeah, it's fine. The details are a bit weird. So okay, yeah, that's another thing for. Okay, I'm gonna say this. So I use code to solve the differential equation, and then for, so the third thing I did was fitting model to data. So here I basically defined a loss function, right? So what I wanted to do here was I wanted to find an R such that that R models the balance in the best way possible, right? It fits with the actual spending data. Right, so here, okay, let me, it's more like, more or less find our, yeah, such that modeled balance best fits actual spending data. So that's something I also need to kind of work on. So it's actually this part because I somehow can't get my carrying capacity to be zero because of this part. If I fit the data based on R, that's I think one of the factors that's preventing me from making it zero. Or because I've just spent less. But we'll see. And I think it also depends on the rate at which I'm spending. And then it's going to sort of simulate. So just based on my rate of spending, it's going to tell me, okay, let's try to fit it, but at the same time, put a carrying capacity. And at the end of the day, I'm not going to get to zero. So that means I probably need to spend more. But anyway, so, okay. So here's what I basically did. I used a loss function, right? I used some loss function that I just got off of Google. Okay. So here what I did was I used a loss function, and here it's called the MSC, or we call it the mean squared error. Let me just write the whole thing. Or MSC. Right? And the purpose of this is actually to, so here's how I fit the model to the data basically. And this is something I'm having an issue with. What this loss function does is it calculates the average squared difference. Calculates that thing. The average squared difference between its predicted and actual values. And then it gets some average, it gives me some number, and then it fits the model there, right? And then there's some other definitions here, which is a common choice for evaluating regression models because it penalizes larger errors more heavily due to squaring process. And it makes the model focus on minimizing those significant discrepancies. So what does this model look like, right? So here's how I kind of looked at it. So my MSC, I put in my R. So this is how I got my R, right? This is how I did it. And so here, yeah, I got R. This is equal to 1 over n. Yeah, I think that was the function there. Yeah, 1 over n, and then this n. So it's a summation thing. And then this n is up here, and I equals 1. Then here's where the thing comes in. So this is my model balance B sub model, right? And I think this was, okay, he wrote it in a weird way. Yeah, what in the world is that? The time at ith observation and the R being fitted. Also, it's used to distinguish independent variables. T from parameters R. Okay, let's just do that. That's fine. I'm still learning notation anyways, but basically it's something like this. So that model at some ti or t sub I, which is independent to my spending rate, minus, okay, it looks complicated now. I'm kidding. And then my actual model, right? So my actual model, which gives me that thing at time I. And then I basically square them, right? Because I subtract them and then I square them and then I do them again and again, right? That's why it's a summation. And then once I do that, I divide it by the number of those values, which is n. And that's how I get R. Or it's actually based on R, I think. But yeah, the mean squared error. That's how it helped me fit the data to the curve. Okay, cool. Right. So here I'm saying, so here are the descriptions of each of them before anyone gets confused. B sub actual is recorded balance, right? So here's the actual balance. At day T sub I. So if T sub 1, then that's probably July 7, something like that. Then we have B model. This one's the simulated value or the modeled value. I really don't want to use the term ordinary differential equation because I have yet to learn it. But this is the simulated value from solving my model, that logistic decay model. Okay. And then from there, I also used code to optimize or quote unquote minimize my mean squared error and find the best value of R, right? And so this is again a SciPy thing. Let me just quickly show it real quick. So here's how I did it. Let me go ahead and go here. Oops, what am I doing? Did I share my screenshot? No way. I shared my screenshot. Okay. Let me go here. Right, this is my code. So here's how I did. So here's how I solved the equation. So okay, let me actually put comments here. This is when I solve the model. This is when I get mean squared error, also known as MSC. And then this is when I find the best R and minimize MSC. Now I'm gonna admit I don't know what this is doing underneath the hood, but based on this one here, this is something that Python does. It basically does minimization of a scalar function of one variable. And so that's what I'm doing here. And I think this is just getting the derivative and then doing something with it, right? Probably that. Yeah. Use this algorithm and stuff like that. But basically finding a local minimum or bisection method, that's one thing. I did talk about bisection method in my scientific computing course. And then you can pass in custom minimization methods. But yeah, I just did it by default because I really don't know how this works. But yeah, I mean, somehow it looks like it's working. But yeah, so something I still need to work on. But yeah, okay. Now going back to my, where in the world am I at? Okay. So what I basically did was, again, I use code to minimize MSC and find the best value of R, right? Okay. And then here's the visualization. So I really wanted to, is there a way I can? Hmm. Okay. So here's the visualization, and I'm still working on this, I would say. So here's the, I think let me show it here. Yeah, it's better to show it here. So here's how the visual looks like, right? This is my actual data, the blue points. So that's the date and my current balance as of that date. And then my red dotted line is my carrying capacity. So that's my K of T. So these are the actual data points. And then my fitted model using mean squared error and finding that best R and minimizing it using the SciPy module of Python, it gives me, well, this best fit. And here, as you can see, this is something I'm still working on, but let me actually show this part. Here, by August 23, that's my balance. By August 23 here, that's my balance, right? So that's the issue with fitting models. I think is when I tried to fit the model, it also affected my carrying capacity as well as this green fitted model, right? And yeah, my best R here in this case is 0.27. I think when I add more data, the model should simulate better in a way, right? So here this was 69 and 24. But let's say if I were to take out some data. Let's say I take out, so these are my data. Let's say, yeah, let's say I take out these ones, right? Say I take it out. That's my new data. If I were to run this whole thing again and just go ahead and wait. Yeah, sorry, Python's slow. Staying forever. All that. 12 seconds, 20 seconds. Okay, that's it. I should stop. 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 Okay. Let me go ahead and just run it one by one. There we go. Yeah, running it one by one helps. Load the data. Successfully loaded from July 28th. So I took out July 7. And then this one, come on. Nice. So here I have lesser data. Yeah, I think this is what makes mathematical theoretical modeling helpful, is if I have lesser data, it gives different, or actually if I, depending on the data, it gives a different simulation every time. So it's really just simulating. Then 27 days before August 24. Okay. And then that fit Up R is 1. Go, 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 go. And there we go. So there, right? So before it was 69. And I should stop. Okay. So before it was 69. Now it's like 49 to 29. Right? So that's the weird. It adjusts based on the model or based on the data that I put in. Right? So it's actually, if I fit this thing and I model this thing, then it would adjust accordingly. See, that's the most surprising thing that I didn't even. I think that's what's fascinating, right? Because this is not, right? Because I don't know stats, right? This is not something like, okay, I put more data, the model improves. It's more like depending on the data, this is the simulation. I think that's what, based on how I'm doing this, that's what I'm getting. So if okay, I don't want to run it all. I put back the data in. So that was like 49.29. If I put more data here, and I said that that was my initial point, come on, come on. Okay, why is it still 27? What the? Oh, I forgot to save. Oops. Let me see. Did I load it? I did not load it. Okay. Import. Yeah, I don't want to run it all when I'm maybe when I'm presenting this. Okay, let me. Yeah, now it's 48. Now it's back to where it was from July 7. 7. I can't do math. July 7 plus 48 days is August 24? Question mark. Okay. And here, if I were to look at my model again back from its original, it's back to 69 and 24, right? So the way that it fits, so the way when this model fits the data, it affects the sort of prediction. I don't know if there's a prediction, the simulation, right? Here it's 16, here it's, or yeah, 69 by August 23, based on the fitted model, right? But if I have like a lesser one, then it kind of also looks at the rate at which I'm spending. And then from there, it simulates it accordingly. As well as my carrying capacity, it adjusts for, I think it adjusts for both, right? And let me see. This one was like what, 20, 24? This one was 69. This one's 24. Yeah. If, let's say, I were to take, I don't know, let's take this one out. Also, me playing around with data, right? So if I were to do this, okay. Yeah, now I have lesser data from August 1 to 3. So here I don't know how it's gonna simulate, but it should tell me. Yeah, now I have 23 days because 3 August 1, right? The starting point, August 1 plus 23 is August 24. Best fit is R, best fit of R is 1. And then here, hold up. So yes, my carrying capacity as well as my fitted model also adjusts based on the data, right? And so yeah, fun stuff, interesting stuff though. I would want to learn more about, for me, how to make a model that learns from the data and gives more accurate predictions and not just simulate. I would want to learn more about how that works. So maybe do stats. Yeah, maybe I'm gonna do stats, but yeah. Here it's, yeah, 24, 69. Yeah. Yeah, it's pretty much what I'm doing basically. So that's the visualization part. It's basically just look at code. Yeah. Okay. And then from there, So I guess, what am I doing? What am I doing? What am I doing? I'm trying to make a write up. Oops. Uh-oh. I think I messed up. Okay, never mind. I didn't. Okay, so that's for the visualization, right? It tells us the. Am I doing it here? Yeah, I'm doing a write up. So basically, we plotted the actual versus modeled balance or simulated balance. My carrying capacity over time, which decreases linearly. Yeah, as well as hoverable and zoomable features. It's basically just those stuff pretty much. And I'm gonna go through them in the actual presentation. I might even send this video. Oh no, we'll see how it goes. And so here's what the and then here is, I guess, like results-ish. So here's that. Oh my god, why is this weird? So how do I interpret this model, right? Well, here we see that there is an overall trend of decreasing balance, right? There's that. And then there's this concept of spending slowing down as budget diminishes, right? And then the idea that spending should approach zero as the end of the dining plan nears. This is something I'm still working on. And then for my, yeah, that's model interpretation. Then this is my limitations. So the limitations of this model is that it does not account for irregular or impulsive spending. Actually doesn't, right? So for instance, it would be something like sudden big purchases, something like that. Doesn't take into account that part. So like let's say, oh, I bought like a I bought a Gucci bag which cost like 100 using my dining plan, which is technically not possible because that's only for food. Something like that. And then here it kind of assumes a smooth and continuous rate, which isn't true for real life discrete transactions, right? Because in some days I won't spend anything, So that's usually on the weekends, which I didn't take into account in my model as well. So usually at the end of the day, it would depend, right? And then also I chose a linear decline of carrying capacity because I think it's a reasonable guess or assumption. I could have chosen like an exponential decline. Still works, but I think that's more of the model's job to do. So maybe just a linear decline would help. Just because I just think it's a reasonable guess for the most part, right? But again, it may not reflect actual planned rate of consumption. It's also another thing I need to look for. Because definitely that's very unrealistic, I would say. We cannot keep, so again, just to reiterate my point, we cannot consistently spend the same amount of money per day. Sometimes we don't spend at all, sometimes we spend more than we usually spend, stuff like that. It's just not realistic. Okay. Then we also talked about something, I guess, about data sensitivity, which is again also an issue that I'm working on because I don't know how to do a model that improves if we're given more data. So this begs the question of, I guess, how much data is enough, right? And I guess for this type of model, we're seeing, I guess, early and mid stage are most valuable, right? So we're seeing that mostly the early and the mid stage. Then we can simulate from there, right? Another thing is that too little data for the curve fitting part can lead to poor estimation of R. And then too much late data could skew the fit, right? Or it could affect the fit. If the spending behavior changes. So like, I don't know, panic spending, panic buying. Okay. And then let's do a conclusion. So for my conclusion, actually, do I need a conclusion? hmm Or okay, maybe not conclusion, maybe summary. Summary. Let's do possible extensions. Actually, yeah, let's do summary. So just to summarize, so just to reiterate what this model does. So it basically simulates spending behavior in a principled way. And then it also adjusts its kind of shape or how the curve looks like via R from data, right? So those are from the data points, use mean squared error and stuff like that, optimization using SciPy from Python and stuff like that. Then here it basically, so this is the, I think, most important part, is it enables forecasting and as well as visualization to help us determine where if we're kind of on track to fully use funds by deadline. And some possible extensions of this, because not everything in math ends. Once something's beginning, it never ends. So possible extensions of this would be maybe non-linear decline of carrying capacity. Maybe like an exponential decline. I was thinking of that. What would happen? I don't know. I haven't tried it in carrying capacity. So for instance, maybe yeah, maybe something like quadratic, but just using a part of it. Or maybe exponential, right? It's also one more thing. Another suggestion maybe um fit a piecewise R. Do you think it's possible? Like let's say for this point, or because sometimes just to take into account like if my behavior spending changes, like a piecewise R. Just to take into account, let's say the panic buying and stuff like that. Spending behavior, right? So instead of it being like a fixed R for everything, right? That's also another thing. Then yeah, maybe take into consideration the so that's something I didn't do. Day of the week. I don't know how I'm gonna do this, but something like this. So here we say that students spend more on Monday to Friday. And then another thing, maybe, yeah, yeah, I think those are enough suggestions. Maybe. But yeah, those are some ideas I was thinking of. Right? Okay, so that's it for this kind of working on my write up for budgeting analysis using logistic decay model. Yeah, I hope you guys enjoyed. I hope this was very interesting. To me, it's very interesting. And yeah, I hope you guys model your own problems. Thank you. I hope you guys enjoyed, learned a lot, and I'll see you all in the next video.